nutshell. Range is similar. Range is to y as domain is to x, if you want to think about it that way. So the range would be all of the y values that a function can have. And we don't have a real effective way to do a range calculation by hand, which is good news for you guys, because then you don't have to worry about doing it by hand without a calculator. So what we're going to do is we're going to talk both domain and range by looking at a graph, because you can do that still. Okay? And if you have a calculator, you can graph whatever the function is, and then you can take a look and see what that range might be, as well as the domain too. So let's try once. So let's take a look at the function f of x equals, let's do 1 over x plus 3. Okay, so take out your calculators, open up your y equals menu, and let's type that in. 1 over x plus 3. So it should look something like that. And if you're, just in case, make sure your window is a standard window too, so we're all kind of looking at the same thing here. All right, and then we'll graph that. Okay, so based on the way that this thing is shaped, we've got some vertical and horizontal asymptotes in here, which you guys studied a little bit in Algebra 2, and we'll talk a lot more about actually tomorrow. But we can use that idea to help us determine what the domain and what the range are. So now the domain of this one, if you just look at the equation that we wrote out, you can probably tell me what that is. What's the only bad number in this function for the domain? 0, right? So our domain should be negative infinity to 0, and then 0 to infinity, hopping over the 0, right? And if you look at the graph, just look along the x-axis here. Do you kind of see that domain on the graph? For some people, it's like, boom, right away. Other people, it kind of takes them some time to sift that out. But think of it like this. As we're moving along, I've got value to the function, value to the function. Then as soon as I get to 0, then there's this gap here. And then it hops over the 0, and then it keeps going, right? And that's that vertical asymptote that's at 0. That's what's happening right there, okay? So you got all these numbers up to 0. We hop over 0, and then it keeps going, okay? And that's the x's, okay? So looking at it kind of left to right is domain. Range, on the other hand, would be going from the bottom to the top. Okay, so looking at what are all the y values that I'm getting as I go up, and am I skipping over any as I do that? Okay, so are there any y values this thing never gets to? 3. Yeah, because there's a horizontal asymptote of 3, right? So it goes, hops over 3, keeps going. So in range for this domain, you guys already told me, negative infinity to 0, union 0 to infinity, based on what we saw on the graph there. So what would be the range then? How would I write that? Yep, you got it. Negative infinity to 3, union 3 to infinity, not including the 3. So we're hopping over that one. Yep, that would be the domain and the range for that. Okay, how about a little simpler function, just x squared. Talk domain and range of x squared. So graph that one real quick. Maybe you already know what this one looks like, but just in case, there's x squared. Okay, now keep in mind, x squared just keeps on going, right? So what's its domain? It's everything, right? Negative infinity to infinity. Okay, look at that graph. What's the range of x squared? 0 to infinity, right? Does x squared ever go negative in the y's? So that's not part of the range then. So here's the question though. 0 to infinity, but does it include the 0? It does, because it actually comes down and hits 0, 0, right? That parabola. So it does include the 0. All right, so the domain and range for x squared then, domain is negative infinity to infinity, and the range is 0 to infinity, but we're going to put a bracket on the 0. Like that. Okay? So that's just, I'm not going to do any more with range, but that's just a couple of examples of how you can go at finding a range of a function. Okay? Just look at the graph, think about what y values is it hitting from top to bottom, and you can do an interval just like you do for domain. Okay, with the brackets and the parentheses and all that kind of stuff. All right. We got a little bit of time. All right, so I can get into continuity just briefly, and then we're going to be done for today. Okay. So, does anybody know what it is to be a continuous function? Say it again. Never ending? Yes and no. It's kind of a more of, not about its start and ending, but more of what's happening in the middle with continuity. If something is continuous, it keeps going, right? There's no breaks in between. Okay? So if something is continuous, think of it this way. It's like you could draw the function without having to pick up your pencil. It just keeps going. But if you had to stop, start again, then that's not continuous. Okay? So let's quickly define that here. So to be continuous, it is a function with no breaks. So think of, you don't pick up your pencil. Okay, so there are some different ways that a function might not be continuous, and that's what we're going to quickly go through here. Yeah? Its domain would have to, its domain is negative infinity to infinity. I can have functions that have that domain but are not continuous. I'll give you an example. So what if I have a function that starts like this? Say that's an open circle, and then right above it is a solid circle, and it keeps going. Okay, so what this is a function that has a jump. Okay, and in fact, this is the first type of discontinuity we're going to talk about anyway, so that's good. But it's not continuous, right? Because it has to stop and then start again. Okay, but its domain is still everything in there. Okay, had this keep going, so it goes to negative infinity. But let's say this is at, I don't know, 2 or something. Okay, so every number before 2 is included until I get to here with the open circle. Does that include the 2? Open circle? No, it's not including the 2. But is this? Yeah. So I've got every number until I get to 2. I do have 2, and then every number after 2. So my domain is everything. I didn't skip anything in my domain. However, the function is not continuous because I still had to jump to start it up again. Okay? So that's a little bit of a tricky thing to this. It doesn't have to have a domain that's negative infinity to infinity. All right? And so in this first type, discontinuity is called a jump discontinuity. All right, so if something is continuous, or if something is not continuous, it has a discontinuity then. Another kind we'll run into that also does not require that the domain be anything different from negative infinity to infinity would be if I had something like this. If I had a function that had a little hole punched in it, and then maybe the function has a value just like floating above it like that. These are pretty rare, but this is called a removable discontinuity. Okay, so if it jumps up, that's a jump. If you've got a hole in the function, that's a removable discontinuity. And then there's the kind today, actually, and that you guys have studied in the past. It's called an infinite discontinuity, but you know it by a different name. You know it by a vertical asymptote. So we had something kind of like this where it has an asymptote that it's approaching, and then maybe it starts up again on the other side of the asymptote and keeps going. Okay, so what's this object here? This is a vertical asymptote, but the type of discontinuity it is called an infinite discontinuity. All right, so that's it. Those are the different ones we've got. So you guys are going to be asked to identify these in your homework if they give you a function. Sometimes it's just you'll have to graph it on the calculator and look at it, that sort of thing, and we'll get into more of that later. But for tomorrow, we're going to be looking at increasing and decreasing intervals, whether functions are bounded, symmetry. We'll talk more asymptotes, and then we will be done. Okay? So you guys can have the rest of the time to hang out here.